All right, good morning. We will do this question from Resnick and Halliday. This question is from the topic of Gauss Law. And it's a tricky question. You don't have long calculations involved in this question. The only thing is you have to apply yourself and think through Gauss very carefully. Let's read the question first. Figure 23 shows in cross section 3 solid cylinders, each of length L and uniform charge Q. Okay, so these are the cylinders. The charge on each one of them is Q, although the distribution of the charge here, the volume it occupies here is the maximum. Okay, so the charge density here is least, the charge density here is medium, and the greatest charge density is here. Remember, these are not point charges, but we will discuss that later. Concentric with each cylinder is a cylindrical Gaussian surface. So that's your cylindrical Gaussian surface. Okay, and your job, what's your target? The target is to rank the Gaussian surfaces according to the electric field at any point on the surface greatest first. Okay, now let's apply the strategy. Obviously, we know the Gauss law is your EDS is equal to Q enclosed divided by permittivity of the medium, right? Let's look into the figure A. If I talk about figure A, the electric field multiplied by ds, which is going to be the curved surface area of the Gaussian surface, 2 pi there is no, okay, but it says that the have the same radius. So let's say the radius is r, the length is l, so 2 pi rl. What is the charge enclosed? Q. Okay, so if you notice in this particular expression, the concept of charge density is not available, right? And I will discuss this. See, generally what happens if you consider this figure, for example, and you would to calculate the electric field inside the sphere with uniform charge density, you would find that the Gaussian surface encloses this much charge. And as the Gaussian surface increases, the electric field increases. And then at the surface, it reaches the peak because the whole charge got enclosed. And after that, because of the distance of the Gaussian surface, the electric field goes down, right? So E is proportional to the distance in this case, as the distance is increasing, and this happens still. So this is the situation which a lot of students confuse with the uniform volume charge distribution, especially when you look into the figure. But this is not a complicated problem at all. The intent of this question is to check your fundamentals. Okay, so this is a Q enclosed divided by epsilon naught, and E is equal to Q upon 2 pi RL into epsilon naught. This is electric field for the figure A. Let's go to figure B. The Gaussian surface is still 2 pi RL, right? The radius I have taken as R. The length again is L, is equal to, the total charge is same. It is clearly mentioned, uniform charge. Okay, do not confuse this question and get carried away by the fact that you have 3 different size of the charge, right? It is typically a misleading kind of situation, right? The figure I've drawn is to just a quick recall for when you have a spherical charge distribution, right? And it's volumetric charge distribution. There is nothing like this in this question. Okay, so this is a cylinder. Okay, this is a cylinder. E is equal to Q enclosed upon epsilon naught. Again, the electric field comes out to be Q, the total charge, divided by 2 pi RL into permittivity of the vacuum. And even if you consider the third figure, you still have the same scenario. EDS is E2 pi RL is equal to Q upon permittivity. There is no difference in the charge enclosed, and that is the spirit of the Gauss law. The question is trying to mislead you and take you into a different tangent by giving you different size of the charge inside. There is no mention of the density, nothing. It's equal charge. The Gaussian surface, curved surface area is identical. The electric field is radial in all the scenarios. Sorry, this is a radial, this is a center. So radial would typically mean this, right? So this is the radial, this is the radial direction of the electric field. So the charge, if you see the answer of electric field, it is identical. So that there is no greatest per se. All the electric fields are identical, they're radial, there is no difference. So this question was a conceptual question. It was not to test your mathematical capability of integrating a scenario where you have a charge distribution, a volumetric charge distribution, stuff like that. So this is not that scenario, but it does look like one. That's a point. So remember, be very careful when you're solving these questions, that you are in control of your emotions and you don't get carried away by the figures. The figures are given differently, and this is to misguide you. But if you apply the basics, your strategy, which is EDS is equal to Q, the Q enclosed is identical, the Gaussian surface is identical. There is no reason why the electric field should be different on the Gaussian surface, despite the fact that the charges are shown in a different manner. It's all about Q enclosed and the Gaussian surface, which was identical. And the answer is all the electric fields are identical. So E1 is equal to E2 is equal to E3. Great question. You can go to my playlist of Gauss and watch some more videos around this topic. So I hope this helps you. If you like this video, give me a thumbs up, and please do subscribe to this channel. You will see many questions pertaining to AP Physics on this channel, which will be very useful to you. A lot of stuff from Resnick and Halliday. Thank you very much for your time.